Okay, let's get started. Today, we're very happy to have Nihar Shah from CMU. Nihar got his PhD from Berkeley, UC Berkeley, a few years ago, and he interned here at MSR and also got the MSR PhD fellowship. And today he has been doing kind of ever since the intern, I believe, right? We started doing with this very interesting interdisciplinary works on crowdsourcing, pricing, and also pricing for crowdsourcing, and works that involve lots of psychology, social science, game theory, you name it. And today he's gonna talk about battling demons in peer review, which I think is a very, very important topic.
Thanks, Lynn, for the kind introduction and for hosting me. I'm going to talk about some work that we have been doing for the past 2 years in my group at CMU, which is on improving peer review. So the state of peer review today was very nicely described in a Nature article by Drummond Rennie. So in this article, it says that peer review is a human system, and hence there are a number of prejudices, there are misunderstandings, there are biases and inefficiencies, it's occasionally corrupt, and overall it says that in short, peer review is unscientific. And survey after survey after survey across a number of different fields in science and engineering show that researchers have an overwhelming desire for improving peer review. And closer to us in computer science, there has been tremendous growth in the number of submissions to our conferences. For example, in NeurIPS, there has been a near exponential growth of a 40% increase every year in the number of submissions. Now, this aspect, coupled with the fact that the number of expert reviewers is not growing as fast, lead to a number of challenges that we have to solve. So in our group, we are looking to tackle the systematic problems or demons that arise in peer review using principled and practical approaches. So in this talk, we'll discuss 5 different issues that arise in peer review, that of subjectivity, miscalibration, biases, strategic behavior, and noise. Each of these issues lead to some sources of unfairness in the peer review systems. And we'll discuss techniques to mitigate these issues. Now, this will also form the outline of this talk. I'll be going into the first part in great detail in subjectivity, on miscalibration in some detail, and I'll give a brief overview of the last 3 parts. And throughout this talk, please feel free to interrupt me if you have any questions, if you have any comments. Just as a side note, while we are focusing on peer review in this talk, these problems in learning from people that I mentioned on the previous slide arise in a number of different applications, including hiring, admissions, A/B testing, crowdsourcing, online grading, etc. And a number of techniques that we develop are applicable to a variety of these applications as well. So with that, let me start with the first topic of subjectivity. And this is joint work with Ritesh Nuthigattu and Aryal Procaccia. So by subjectivity, we mean that different reviewers can have different subjective opinions about the various criteria to be used to judge a paper. For example, let's say there is one reviewer who thinks that novelty is not really useful unless the paper shows an improvement of at least 10% over the state of the art. Whereas, for example, let's say most other reviewers think that novelty is super duper important. Right. Now, if a paper comes along that has really novel ideas, but improves on the state of the art by, let's say, just 4%, then if it goes to this green reviewer, it might get rejected, whereas to most other reviewers, it would have gotten accepted. So in this case, just the outcome, if it goes to say the green reviewer, might be considered as unfair to this paper. So overall, we want to ensure that every paper is judged by the same yardstick. And of course, we want this to be a good yardstick. Any questions so far? All right, so let me formalize the problem setting. So each reviewer is assumed to judge every paper on some k different criteria. Right, so this is a common setting in peer review, and these kinds of criteria are, for example, originality, relevance, impact, significance, writing style, etc. And each reviewer is also asked to provide an overall score for the papers that they are reviewing. In terms of notation, if reviewer I reviews a paper J, then we say that the reviewer provides a vector xij, which is a k-length vector representing the scores it gives to that paper for the k criteria. And the reviewer also provides a scalar yij, which is the overall score that the reviewer provides to the paper. Now, for simplicity here, we assume that all scores are in the interval 0 to 1. Now, we also assume that every reviewer in their own mind has some mapping from the criteria to the overall scores. So, it is some function from 0, 1 to the k to 0, 1. Now, every reviewer can have their own personal subjective mapping. The only thing we assume is that these mappings for each reviewer are coordinate-wise non-decreasing. That is, if let's say everything else being the same, the novelty let's say went up, then the overall score that the reviewer would give should not go down. That's the only assumption. Okay, any questions far? Okay, and now we said we wanted a common yardstick. So in terms of this formalism, we say that we want now to have a common mapping for all papers. All right, in order to do this, we take a data-driven approach, that is to learn a mapping. What do I mean by this? Well, first for every reviewer I, paper J, we get xij and yij, the criteria scores given by that reviewer and the overall score. Now from this data, we will learn a mapping which we will call f hat from criteria scores to overall scores. Once we have this f hat, then what we suggest is that for every review, you take the xij and then replace that yij instead with f hat of xij. Okay. So f hat is the learnt mapping from criteria scores to overall scores, and this is learnt from all the reviewers combined. On the other hand, yij was the overall score given by the reviewer based on their own subjective mapping. So in order to mitigate subjectivity, we say replace yij with f hat of xij, and now these f hats of xij's can be used by the program chairs to make their decisions however they like. Now the key question here is, how do you learn this mapping? What do I even mean by learning this mapping? Any questions? Yeah.
Just before, so the example you gave for the the one with novelty with 10%. So there, in that case, would be novelty is one of the k criteria, and the improvement, empirical improvement, another criteria.
Yeah.
It's basically this thing.
Yeah. So the experimental state of the art.
We were combined differently than the other.
Perfect.
Okay.
Perfect.
Okay.
Perfect. Perfect.
But also I wanted to understand, like, are you assuming that these monotone mappings can look at interactions between the k criteria?
Yes, so we make no assumptions on these mapping other than them being coordinate-wise monotonic. So they can be highly nonlinear if that's kind of implicitly what you're asking. It is I could have a mapping as a reviewer which says that if novelty is greater than something and clarity is greater than something, only then give a score of 1, otherwise so on. Yes, it can be highly nonlinear or anything.
Then the other bit is like will you empirically show us based on how reviewers actually rated their papers whether this is a reasonable fit to how they give?
Yes.
Because I'm not even sure that I give consistent mappings. I may like even my own mappings might change from.
I agree with you. We'll come to some empirical evaluations. That said, one thing to keep in mind is that in peer review, there is no notion of ground truth. So we can't really definitively say that yes, at least in the data that we have, that this is better than that. But again, we'll look at some data and see what happens. Great. Any other questions? All right. So let me now specify the framework for learning a mapping. Now just for simplicity in this talk, let's suppose that all reviewers review all papers. Here actual algorithm and so on applies more generally, but this will just help me in my exposition. So now the data that we have from the reviews comprises 2 matrices. Both of them have reviewers as rows and papers as columns. The first matrix is the matrix of criteria scores, xij's. That is, the ijth entry of this matrix is the vector of criteria scores given by reviewer I to paper j. The second matrix is the matrix of overall scores. The ijth entry here is yij. That is the overall score given by reviewer I to paper j. Okay. Now, ideally, if all the reviewers had the same mapping, okay, everybody was on the same page, then there would have been some f such that f of the first matrix equals the second matrix. Right. This is an ideal scenario where there were no problems. Of course, the problem that we are dealing with is that of subjectivity, which means that there is no such common f. Right. And that's why in our learning framework, we do the next best thing, that is find the function f in a reasonable class script f that I'll define in a minute, such that f of the criteria score matrix is as close to the overall score matrix as possible. And we'll measure this closeness in terms of a certain loss that also I'll come to in a minute. Okay, any questions so far? Okay, now in order to complete this description, I need to specify to you what this function script f is and what is this loss. So the function script f is simple. It's just the set of all coordinate wise non-decreasing functions. Okay, that's it. So I'm not assuming any linearity, I'm not assuming any Lipschitzness, nothing. It's just coordinate wise non-decreasing functions. Now, in order to complete my description, I need to specify to you what's this loss, this LPQ loss. So at a higher level, this LPQ loss is a loss on matrices, which is just a natural matrix extension of the standard LP losses on vectors, or LP norms on vectors. So more formally, the LPQ loss is a family with 2 parameters, P and Q, each of which take values between 1 and infinity. So think of the analogy to the LP loss family on vectors, which has just one parameter P, which takes values from 1 through infinity. Right, this is the matrix extension. And now, given such a matrix, how do you compute this LPQ loss? Well, it's simple. You take the first row and compute the LP norm of that. So that's just the standard vector LP norm. Take the second row, compute that LP norm, and so on. For every row, you compute the LP norm. And then for the resulting values, you get a column, compute the LQ norm of that, and that gives you the LPQ norm of this matrix. Okay, any questions? This is just a matrix extension of the standard LP losses of vectors. Now this LPQ loss is used in a variety of different applications in machine learning, signal processing, and so on. And in the various applications, they use different values of P and Q. And in various papers, they propose some heuristic arguments or the other about justifying why they use that specific P and Q. Now, as we know, in machine learning, it very often happens that the choice of the loss function can significantly dictate the outcome. And therefore, here we want to take a principled approach to decide which loss function we should use. In order to address this question in a principled manner, we are going to take a perspective from social choice theory, which I'll come to in a minute. But before that, I just want to say that this perspective that we are taking and this approach can be useful not just for choosing loss functions here, but potentially to decide in a principled manner on how to choose loss function in potentially many other ML applications as well.
Before we go into that, I'm still puzzled by the way you formulated the problem, right? Like, can you help me understand what goes wrong if I instead think of each of the reviewers having their own F?
Yes.
Let me call that F sub R.
Yes.
And what I try to do is I try to learn it's like a non-parametric set of reviewer specific mappings.
Yes.
And then I try to just like invert the FR that they may have used to get something where, like, I mean, so this is trying to fit something that's like, like if there are two reviewers who are like sort of completely like oppositely aligned, then I'm trying to fit one F overall, which might just throw out both their unique.
So a few things. So first thing is learning each reviewer's individual F is nearly impossible because you have very little data. Like you as a reviewer reviewing just say 5, 6, 10 papers, and then if you have to learn a 10-dimensional function about you, can't really do that, right? That's one. Second thing is that you're right. So here what we are trying to do is learn a single F. In practice, you could have, say, in a conference where you have theory and applications, you could do it separately for theory and applications. If you as a program chair think that these two areas need different emphasis. So this is a vanilla version which can be modified to that. And the third thing is we deliberately choose this LPQ framework where we don't necessarily set P equals to Q to provide asymmetry across reviewers and papers. So here you see that for every reviewer, you have this LP norm, and across them there is an LQ norm. So that does provide in some way a different emphasis on every reviewer.
Can you just go through what could happen if I have two reviewers who have exactly opposite opinions on every criterion, right? Like, so one of them rates, like, say, novelty extremely high and importance 0, and the other vice versa.
Yes.
Then, if I try to fit a single F, will I end up learning that like both are irrelevant or both are relevant or something like that? Like, what will happen?
We will come to something like that later. Let me think. We'll come to an example.
Be most relevant to a less extent. I think
Is that, I mean, basically, I want to understand like how the PQ loss will interact with it.
So it will kind of average things out. What we can do is we'll come to that in a few minutes. Great. Any other questions? All right. So here we are going to take an approach from social choice theory, which is generally called an axiomatic approach. Okay. So in an axiomatic approach, what we do is we'll first identify some scenarios or special cases that are easy for us humans to reason about. Once we have identified these scenarios, then based on these scenarios, we'll establish certain necessary conditions or axioms that we want from our algorithm. And the hope is that establishing these necessary conditions will help us narrow down in the choice of possibilities that we are looking through. Now, first, let's identify some scenarios that are easier to reason about for us humans. So in this scenario, let's consider the special case where every paper gets the same criteria score from all reviewers. So for example, paper 1 gets X11 criteria score from reviewer 1, and you consider the special case where that is equal to X21, which is the criteria score from reviewer 2, equal to X31, and so on. Likewise, for paper 2, all the criteria scores are equal, and so on. Yeah. So just to simplify notation, we'll let X1 denote the criteria score for paper 1 now, X2 denote the criteria score for paper 2, and so on. Yeah. So this is the special case that we'll consider now. Any questions? Okay. Now that we have identified a scenario, special case, let's establish some conditions that I'll at least like to argue that they are quite natural. And we'll impose 3 axioms. The first axiom is what is called consensus. It says that for some vector x and some scalar y, if you see in the data that every reviewer has mapped that particular x to that particular y, then the learnt mapping f hat should also respect that, which means f hat of x should also be y. Any questions? Okay. The second axiom is called dominance. The formal definition is here, but for now I'll just give a higher level picture of what this means, and in 2 slides from now we'll go into much more detail. So at a higher level, dominance says that if there are 2 papers A and B, and if paper A from the reviews is clearly better than paper B, then f hat of XA should be at least as much as f hat of XB. Any questions?
What
Yeah.
do you say in sorted order?
Yes. So
Is
I'll
each coordinate wise, if for example, I could have the each coordinate larger than one, but if you sort them, then maybe not. So that's
yes. I'll come to that in just a couple of slides. So hold on, I'll come to that in a couple of slides. We'll make it like very precise, and we'll do an actual example that we use in the proofs. Great. And the third axiom is called strategy proofness. The formal definition is a mouthful, but let me just tell you the higher level. So here I am a reviewer, and I know that there is going to be some learning algorithm employed which will take in all the review data and learn a common mapping. Right? This common mapping is considered to be, say, the community consensus on what criteria are more important, what is less important, and so on. This is going to be used for the decisions, etc. So now I as a reviewer will be happier if this learnt mapping f hat is closer to my own mapping, right? And so I might be incentivized to manipulate the reviews that I give in order to bring the learnt mapping closer to my own mapping. So what strategy proofness says is that this should not be possible. That is, I as a reviewer should not be able to lie about the reviews that I provide in order to bring the learnt mapping closer to my own mapping. Any questions?
I'm just wondering if the example I'm thinking about are situations where I actually often when I'm reviewing, it's not about establishing the true quality of the paper, but more about the relative merits. Like I want to sort of figure out where to draw the accept reject bar, right? Part of your framework allows me to do that by employing any monotone function. So for example, I could have something that's very flat and then suddenly shoots up to the higher thing. So that's good. But I'm wondering if some of these things where if I assume that every reviewer has given the same criterion score for this, then technically, like as an area chair, I haven't done a good job of getting good reviews. And I want like some diversity in opinion, or like, and I'm wondering if there is an inherent tension or whether it's compatible with these
Right.
assumptions.
Right. So one thing is that this special case is only created in order to reason about these things. If we let things go wild, then it will be hard to state anything that we require from it, because it will require tons and tons of conditions. So that's the only reason what is done. In practice, we don't assume that this is occurring and so on. A second thing is, maybe a part of your question is also about calibration. Right. Calibration is something that we do address, and I'll come to that in the second part of the talk. Great. Any other questions? All right. So now, from social choice theory, we established these three axioms, and our goal is to use these three conditions to hopefully narrow down on our choice of loss functions to something more manageable. It turns out, as we show, that in fact it narrows down to just one option. That is, we show that the L11 loss is the only loss in the entire LPQ family which can satisfy these three natural conditions. There is nothing else. In particular, we show that if Q in the LPQ loss was greater than 1, then it violates strategy proofness. If P is infinity and Q is 1, it violates consensus. And if P is between 1 and infinity and Q is 1, then it violates dominance. Okay, so L11 is the only one which satisfies this and nothing else.
L1 basically just add everything up.
Add the losses up, yes. Yes. So although a priori, as we discussed a few moments ago, we let P and Q be different, it turns out that if you believe in those three axioms, then you should set P equals Q and that equal to 1.
Yeah. The natural question is, are those set of axioms complete? I could imagine some other special case and that gives me one additional axiom, and maybe L11 does not satisfy that axiom, in which case then
possibly
it's not that
possibly
L11 is special.
Yeah. So in general, in these, it's hard to define anything as complete because that's also subjective. You might want something more, I might want something less. At least in our work, we identified these three, and it turned out that this was the only one. We did identify a few more. It turned out L11 satisfied those as well. Great. Any other questions? And in particular, one thing that we found was this violation of dominance was quite paradoxical. And in the next slide, I'll tell you about why at least we found this to be surprising and paradoxical, and also what this dominance is in more detail. Okay. So let's look at dominance, and in this slide, let's look at a specific loss where P equals to Q equals 1. So this is the L21 loss. Okay, P equals to Q equals 1, meaning that for every reviewer you take the L2 loss and then add these up. So that's a very natural loss. Now let's see what happens. So let's say there are two papers. Let's say there are three reviewers, and let's say K equals 2. That is, there are two criteria. Let's say the criteria scores given to the two papers are x1 for paper 1 being 1/4, 3/4. So this is the vector of criteria scores given by all reviewers to paper 1, and x2 being 3/4, 1/4 is the vector of criteria scores given by all reviewers to paper 2.
They're the same three reviewers?
Same three reviewers, yes. So the three reviewers review both papers, yes.
So they give the same score?
Yes, to each paper they give the same score.
Okay.
Yes. So, okay. And now these are the overall scores given by the reviewers to papers. So reviewer 1 gives a score of 0 to both papers. Reviewer 2 gives a score of 1 to paper 1 and 0 to paper 2. Reviewer 3 gives a score of 0 to paper 1 and some z smaller than 1 to paper 2. Now let me ask you one question. given, suppose that you have just this data and nothing else. Okay, suppose you know only this, and now you have to accept one of the two papers. Which one would you accept? This is all you know. Paper 1. People seem to think paper 1. Anyone for paper 2?
Only if I wanted to irritate reviewer too.
Yeah.
Doesn't this seem like a bit of an artificially thin account, right? Like so without it feels like we're putting too much importance on putting a total ordering on the papers just based on these numerical scores. If I'm trying to make a selection, aren't there a lot of criteria I should be looking at beyond the numerical?
Sure. Yeah. What we have done here is that what we are saying is let's identify some special scenarios in which we can reason about well. So this is one special case scenario which we are identifying, through which now we can try to say what properties we need from the learning algorithm. So the specification will be that if you happen to be in this scenario, then here is what you should do in the learning algorithm. Okay, so I guess anyone for paper 2, paper 1, any other comments? Okay, so here paper 1, in terms of what we discussed, paper 1 dominates paper 2. One way to see it is that the criteria scores are symmetric, and the overall scores, if you see, you have 100 for paper 1 and something smaller than 100 for paper 2. Right, so paper 1 dominates paper 2, and hence what you would like to have is your learnt mapping f hat should map paper 1 to at least something as big as paper 2. Okay. So now let's see what happens if you try to learn under the L21 loss. Now this learning is closely connected to what is called the Fermat point of a triangle. So what's the Fermat point of a triangle? So you're given a triangle. Now consider any point in this space and compute the Euclidean distance of that point to all three vertices and add up the three distances. The point which has the minimum sum of Euclidean distances to the three vertices is called the Fermat point of the triangle. Now it turns out that if you take a triangle with these three rows as the three vertices, then f hat x1, f hat x2 under the L21 loss minimization is exactly the Fermat point of this triangle. The reason intuitively is that if you consider any point, in the Fermat point we are looking at Euclidean distances to the three vertices. That's the L2 part, Euclidean distance, and then we were adding the 3 up. That's the 1 part. All right. So now what happens to the Fermat point of this triangle? So if z was equal to 1, then the Fermat point is 0.2, 0.2, which is fine, nothing alarming. Interestingly, now if we bring this vertex down, top vertex down, and make z equals half, then interestingly it turns out that the Fermat point moves much more to the left than down. So the Fermat point now becomes 0.12, 0.15, which implies that here f hat x1 is smaller than f hat of x2, and hence L21 violates dominance. Okay, it violates the condition that we needed. Any other questions? All right, so this completes the technical part on subjectivity. Now, we tried this on peer review data from ICHCAI 2017, and what I'm about to show you are just some plots just for fun to see what this learnt mapping looked like. So ICHCAI had 5 different criteria, and I'm going to plot some cross sections of it, representative cross sections. So first thing that we found was in terms of writing and relevance, if either of them were really bad, then that was a significant downside for the paper. If either of them are really good, then they were appreciated by the reviewers. But in between, there was a big plateau where it didn't really matter. We saw that technical quality and significance were mostly linear and accounted a lot for the final scores. And originality had a moderate influence. Yeah. Towards your question, Adit, one earlier question, so we found that if you take the learnt mappings and now for every paper you take the average, the mean of the learnt mapping from all reviewers and sort the papers according to that, then that agreed 80% with the actual accept decisions. Or 79 point something percent. Now, is that good or bad? It's subjective.
We could ask how well does that compare to just taking the raw average of the reviewer scores? Did that correlate well with the?
Yeah, so the question is like, let's say we get that as 70% or 85%. How do we again say whether it was better or worse, right? So that's something that we have to encounter repeatedly. That is, there is no ground truth which we can say that yes, this is definitely better or worse. Any other questions? All right. So now that completes the part on subjectivity. Now let me talk about miscalibration. This is joint work with my PhD student Jingyan Wang. So miscalibration in ratings is a well-known phenomenon. For example, say a 6 out of 10 for you might mean something quite different from a 6 out of 10 from me. Right? In a peer review context, if a paper goes to a reviewer who's lenient versus if a paper goes to somebody who's strict, it might result in very different outcomes. And this is a well-known phenomenon in the literature. For example, Mitliagakis et al. Say that just raw ratings without other information is potentially useless. Amar et al. Say that these rating scales and ratings are often arbitrary and inconsistent. And the seminal paper by Freund et al. Says that using rankings instead of ratings is very important because different people might even use completely different ranges of scores to express the same preferences. Now, in the literature, there have been 2 approaches towards addressing this problem of miscalibration. The first approach is to assume some simplified models for calibration. However, at least recently in some conferences, people found that this didn't work so well. And one issue is that these models are highly simplistic. A second approach is to use rankings, that is either directly elicit rankings from the people or convert their ratings into a ranking and then use them. And this is commonly believed to be the best possible option if you cannot make additional assumptions about the miscalibration. So the question that we ask here is whether it is even possible to do better than rankings with essentially no assumptions on the miscalibration. We question this folklore belief of whether the rankings are the best possible option or can we do something better using the ratings. So in this talk, I'm going to discuss a simple setting, which I call a 2x2 setting. So there are 2 papers and 2 reviewers. Both papers have some true quality. Let's say Z star A and Z star B. And now the true reviewers are miscalibrated. So the first reviewer has some calibration function, say f1, which maps 0, 1 to 0, 1. What this means is that if this reviewer gets some paper, say I, whose true score is z star I, then this reviewer will instead output f1 of z star I. Likewise, the second reviewer has some calibration function f2, and this reviewer will output f2 of z star I. Any questions?
And F2 also assume monotone?
Monotone, yes, I'll come to that in a minute, yes. Okay, great, any questions? All right, now we don't want to make any assumptions except for monotonicity. So we let an adversary come and choose z star A, z star B, f1 and f2. The only constraint that we have is f1 and f2 should be strictly monotonic. And now let's suppose that exactly one paper is assigned to each reviewer at random. So with 50% chance, paper A goes to blue, paper B goes to green reviewer, 50% chance the other way. And now both reviewers give their scores. So let's say y1 is the score given by reviewer 1, y2 is the score given by reviewer 2. And the goal is, given this y1, y2 and the knowledge of who reviewed which paper, you want to estimate which of the two papers is better in the ground truth quality. Okay. Any questions? All right. Now an important note is that here each reviewer is reviewing just one paper. So if you try to elicit a ranking from the reviewer for the papers that she or he is reviewing, this is vacuous. Right? There is nothing like a ranking of just one paper. So if you were to elicit rankings, then for your goal, you would have at best a 50% chance of success. Any questions? Okay. So now we want to see if we can do anything better. It turns out if you want to use deterministic estimators, then we show that you can't really do anything better. But obviously the question still remains, can we do better than random guessing by using possibly randomized estimators? And using inspiration from Stein's phenomenon, empirical Bayes and Cover's envelope problem, we design an estimator that we show can strictly outperform random guessing. And the estimator is a randomized one, and it's a very simple one to describe in this toy example. So you take the two scores y1 and y2 from the two reviewers, compute their absolute difference, and then with probability 1 plus that absolute difference by 2, you pick the paper which had received the higher score and declare that as the winner. That's the estimator, and it performs strictly better than random guessing, okay, which is what you would have got from ranking. So what we showed is that even if the miscalibration is arbitrary or adversarial, the ratings can provide better estimates, strictly better estimates than rankings. And this was a 2x2 example, but we use this as a building block for more general settings as well. Okay, any questions about this part?
So what is exactly rating here mean?
Rating is you get these numbers, y1 and y2. So each reviewer, say reviewer 1, if the reviewer gets, say, paper I with a true score z star I, the reviewer outputs f1 of z star I. The reviewer gives a score. A ranking means that each reviewer is asked to give a total ranking of the papers that they are reviewing. In this 2x2 example, that is vacuous because each reviewer is reviewing just one paper. Hence, in this example, if you were to elicit just rankings, your final success probability will be at best a half.
And the score is the total score that the reviewer is giving to the paper?
That's correct. That's correct.
So would that for two, if both reviewer review both papers, then
Yeah.
how do you compare with the rating?
Yes. So even then what we can show is that you can perform strictly better Although that's a more detailed discussion which I'm happy to have offline. Yeah. Yeah.
Follow out, what is the gap? Like, how much better than random guessing can you get?
That depends on these calibration functions. So right now we have not made any assumptions. If you can make assumptions, then you can show bounded gaps and etc. Right now our result is that you can just do strictly better. Great. Any other questions? Okay, so let me move on to this part on biases. So in the next three parts, I'll be very short, like just a couple of slides each. So this is joint work with my PhD student Ivan Stelmach and with Aarti Singh. So there is a lot of debate in a variety of academic communities on single blind versus double blind reviewing. Single blind means where the reviewers know the identities of the authors, and double blind is where reviewers do not know identities of the authors. Right. So there could be biases when you know the authors. That could be biases with respect to gender, with respect to race, with respect to how famous authors are, etc. And there is a lot of debate about this in many communities. One argument that is often made in favor of, possibly in favor of whatever is being done or in favor of status quo, is where is the evidence of the existence of biases in my conference? Right? So our goal in this part is to design tests and experimental setups so that we can rigorously test for biases in peer review. And an important challenge here is that we cannot just do a standard randomized control trial, which would require, say, assigning random reviewers to papers, right? We can't do that. So we also have to ensure that the review process is still good enough and that the workload of reviewers is not increased significantly and so on. So we have to keep these practical constraints in mind. Now, a starting point was a remarkable experiment performed in Wisdom 2017 conference, where the program chairs took the pool of all reviewers, partitioned them into two groups. One group was single blind, the other group was double blind. And then for every paper, they assigned two reviewers from the single blind setting, two reviewers from the double blind setting. Now, for every paper, they have access to information about race, gender, fame, etc. And they have reviews or scores from both single blind and double blind settings. Using this, now they conducted certain tests to evaluate whether there are biases or not. Okay. So this was our starting point. But our first set of results is negative. That is, with their specific experimental setups and testing procedures, we found a number of issues that can lead to either spurious false positives or significant misdetections. For example, so let's say that you want to cap the false alarm probability to be, let's say, at 0.05. So that's the specified level. Even then, we show that under very natural conditions, under their setup, the false alarm probability could go very high. On the positive side, we then designed an experimental testing setup which requires minimal changes to the current peer review process so that the quality of peer review remains good. And we designed associated non-parametric statistical tests with strong and rigorous guarantees. So for our test, if we look at the false alarm probability, it's guaranteed to remain capped at whatever is the specified level. And now even if you look at the power or the probability of detection, so here higher is better. Under very natural conditions, we can get significantly higher power. And finally, their tests require a lot of assumptions. And we show that even if all of their assumptions are met, our tests still perform quite comparable to them. So now, given this, we now have a rigorous set of experimental procedures and statistical tests that if tomorrow some other program chairs want to conduct tests for this important issue of single versus double blind, and they can use it for and have rigorous guarantees over it. Any questions?
What did they find?
So their conclusions were that there is bias with respect to affiliation, bias with respect to fame of authors, and regarding gender bias, if I remember correctly, they said that through their data they did not see a bias, but they combined with some other data and did a meta-analysis in which they actually saw a bias with respect to gender as well. Great. Another topic that we are working on is strategic behavior. This is with Han Zhao, Yichang Xu, and Xiaofei Shi. And the motivation is quite simple. So if I am a reviewer and I have submitted a paper to the conference, I am incentivized to say give a lower score to the paper that I am reviewing in order to get my own paper gets accepted, right? And a bunch of people are grinning here. In fact, like there is substantial evidence of such kinds of strategic behavior, and the question that we ask is how do we ensure strategy proofness in peer review? So at a higher level, what we do is we provide a framework for strategy proof peer review, that is some changes in the peer review process with which we can ensure that for any reviewer, the reviews that they provide cannot influence the decision of their own paper. Now, this framework does require some certain conditions to be met, and we also show some complementary results that if you are far from these conditions, then there is no way you can guarantee strategy proofness. And finally, from some ICLEAR 2016 data, we perform an empirical evaluation from which we see that at least the conditions that were required for our positive results do hold in this data. And finally, for the last 2 minutes, we also look at issues of noise. This is again with my student Ivan Stelmark and with Aarti Singh. And by noise here, we mean poor reviews due to an inappropriate assignment of reviewers to papers. So currently, a lot of these big conferences use automated assignment systems like the Toronto paper matching system. But these matching systems, these methods are quite unfair. That is, it can assign, say, all very good reviewers to one paper and all very bad reviewers to another paper, okay, which can lead to unfairness to some papers. Moreover, these don't have any overall guarantees on the overall process. That is, if you look at the overall process, how well does it help recognize the good papers from the bad and so on. So the question that we ask is, how do we assign reviewers to papers, ensuring fairness and accuracy? And we propose an assignment algorithm which can guarantee fairness and guarantee statistical accuracy under certain standard models. And we tried it on ICLEAR 2016 data, and what we found was that in terms of some standard metrics on fairness, it improves upon TPMS by 25%. And if you consider the TPMS objective, which is the average quality, it goes down by 2%. This is the trade-off with respect to TPMS question.
Isn't there a third very important quality, which is reviewer satisfaction with the whole process?
That's correct, and that's something that we are currently looking at. This especially relates to how you do bidding and then how bidding translates to assignment. So that's something that I haven't spoken about here, but I can talk to you offline. Great. Any other questions? Yeah. So overall, there is an urgent need to revamp and potentially at least semi-automate peer review. And we did this work with NeurIPS 2016 program chairs, where we analyzed the NeurIPS 2016 data, and we made a number of observations that at least I think were quite surprising, and that also leads to a bunch of open problems. So some of the works here are motivated by that. We are taking principled and practical approaches, and we are also working towards some real-world impact here. And the papers are available on archive on my website, and if you're interested, you can go to tinyurl.com/peerreviewcmu for a short 4-page survey. With that, I'll stop here. Thank you. Happy to take questions. Yeah?
One from the result on adversary proof, like the 1 plus mod y1 minus y2 by 2. So that assumes a random assignment of papers to reviewers. Have you thought about composing that with how you would try to get good assignments too, right?
Yeah, so that's a good question. So honestly, this was a worst case calibration. That is, you have an adversarial setting where we have to do randomness. We have to think whether if we make some assumptions, if it's not an adversarial setting, then do we necessarily need randomness or not? I don't know at this point. In practice, like let's say you want to do a good assignment like how it's currently done, but you also want to guard against these issues, then what might work is you do your TPMS assignment or our assignment algorithm and then do a small random perturbation. So here you had that, I mean, this was just a 2x2 case where you had a uniformly random assignment and so on. But there you could do a small perturbation where again you have 2 close enough reviewers and papers and you could do uniformly random. Yes?
So in all of this work, we always assume that the calibration function is being calculated on the given conference, right? But conference is like you have a history of like every reviewer reviewing a bunch of data. Like so, like is there any way that you can actually use that data, which is actually what might be more useful for like this stuff?
That's a very good question. Unfortunately, the logistics of that are very, very hard because the data for NeurIPS 2016 is with NeurIPS 2016. The data for NeurIPS 2017 is with NeurIPS 2017 and so on. So there are some coordinations across that, but at least I don't know of there being a systematic set of logistics to streamline that entire process. Yeah, but if we could do that, then that will be much more useful.
Also, does the open review system, which is basically the ICRR stuff, does that like change some things? Like, did you ever observe in your like evaluations whether that was like somewhat different than like all closed form systems?
Yeah, so that's a good question. So for at least in the kinds of analysis that we looked at, we didn't see so much of a difference. Although there are some other benefits that could be possible in open review. For example, things like self-selection, right? Does open review lead to self-selection of paper submissions? Because the authors know that the paper is going to be online forever. So they may not submit bad papers and so on. Possible?
Self-selection?
Self-selection means that, so now let's say there's an author and if the paper is not in a good enough state, but if the deadline comes, say in NeurIPS, they might still submit the paper because if it gets rejected, there is not much harm done. On the other hand, in open review, if you submit a paper, then it's there online always with your name. Okay, so if you are more incentivized to not submit a bad paper. So that's self-selection, that you would self-impose a censorship about what you submit. So these are things, so we are talking to open review folks to potentially test these things, and that's a very good question, that what differences has that made. So one is possibly self-selection. There could be other biases as well. Yeah, any other questions?
Let's thank Nihar again.
Thank you.